So let's get to the Dirichlet problem in a disk and the Poisson kernel, which is the way that the Dirichlet problem in a disk is solved. So what is the Dirichlet problem? Or at least the most basic version of the Dirichlet problem. Sometimes it's applied to a more general problem. But anyway, for harmonic functions, let's suppose that we have an open set in C. We have continuous function defined on the boundary. The problem is to find a continuous function on the closure, right? So it should be continuous up to the boundary. It's supposed to be harmonic inside of U, right? So f restricted to U is supposed to be harmonic, and its boundary values are supposed to be this given function little u, right? Now, this is solvable for many different u. Generally, if u has nice boundary, then it is solvable. That's one way to put it. We won't go into that. We'll only solve it for a disk. But in any case, if the solution exists, it's unique. Well, at least for bounded domains. So suppose that we have a bounded domain, right? And we have two solutions, f and g, of some Dirichlet problem, and they're solutions to the same Dirichlet problem, right? They are equal on the boundary. Then they're actually equal on all of u. Now it's just the maximum principle. You just apply it to f minus g. F minus g is still harmonic at 0 on the boundary, and on a bounded domain, the maximum principle just gives you that it has to be 0 inside. That is not true for an unbounded domain. I'll leave that. There's an exercise in the notes that basically gets you this. Gets you a counterexample for an unbounded domain. So, what is the Poisson kernel? The way that we're gonna solve the Dirichlet problem. Right? We're gonna really integrate against this function. So it's a function of it's sort of traditionally given as p sub r theta, and it's really given in polar coordinates. There's a couple of ways to write it, and they're useful for different things. So either this is sort of a way of writing it in polar coordinates in terms of r and theta, and we can sort of write it like this in terms of r e to the I theta, which means that if we think of it as a function of z, which is r e to the I theta, it's really just 1 over 2 pi, the real part of 1 plus z divided by 1 minus z. So that's really the Poisson kernel. So, and it's defined in, this is in the unit disk, right? So r is less than 1. Otherwise, you'd have you'd have something blowing up over here, right? The denominator would go to 0, and you can actually see it on the graph. The denominator, there's a this function, of course, has a pole at 1, and that's where you get this peak. It just blows up. Of course, this is cut off at some point. It goes off towards infinity. It's of course finite everywhere inside, but as you go towards the boundary towards 1, then it's it blows up, right? So that's the way that it looks. right? It's sort of a peak that grows towards the 1, right? Now, let's prove some properties of the Poisson kernel. Some basic properties. It's really, the Poisson kernel is an approximate delta function, and it's a nice approximate delta function on the circle. So what does that mean? Well, first, this is this idea that it's a nice delta function, approximate delta function, not just any. It's a positive one, right? So it's always positive, anywhere on the disk, right? And again, we're only looking inside the disk, right? So it's for all r and all theta. Furthermore, if we fix r, any r between 0 and 1, then it integrates, the Poisson kernel integrates to 1 if we integrate in theta, right? And finally, it's, if we look at, if we basically take out small neighborhood minus delta to delta and look at the rest of the thetas, so the rest of the thetas are this thing. So for any fixed delta, if we look at the thetas in these two ranges, then the Poisson kernel, if we look at the maximum of it over these two ranges, it will go to 0 as r goes to 1, right? This is for a fixed theta, right? So fixed delta. So for fixed delta, for theta in this range, for the two intervals, we get that that the supremum of the Poisson kernel goes to 0. Of course, the infimum is 0. So because it's always positive, right? So we actually get that the Poisson kernel on these two intervals for any fixed delta goes uniformly to 0. Of course, it does not go uniformly to 0 on all of minus pi to pi. And actually, it's a good thing to look at a graph of p sub r for various r. So in this in this picture over here, this is p sub r for 3 different r's. So r 0.5, that's this blue smallest peak over here. It's sort of a wider peak. It's sort of bigger than the other ones up until we get here, right? Right, this is where it crosses. Maybe let me try to zoom this in, right? You can see it's the blue one is bigger than the green one is bigger, but the green one is also going to become smaller. And the red one is the smallest one first. It will actually become the largest one near the origin. So the green one is 0.7, and let's see, maybe let me go. Yeah, okay. And the last one, the red one, is 0.85. So basically, as r grows, this peak will get taller and taller, right? So over here we're almost up to 2, and you can see maybe let me go back here, right? You can see that those lines, those are the circles on this graph, right? So you can see how the peak starts growing, and then it's growing more and more and more, right? So now, one thing to notice over here is that this is going to be useful in the graph, that that p sub r is symmetric about the origin. It's even, and actually that follows just from well, we'll see the formula in just a moment again. It's that just follows from the formula, and it's also decreasing as let's say on the positive side, right? So that will actually be useful for this last bit over here, because if we fix any delta and you know we look at you know some range of thetas, then it's actually enough to look at the leftmost point. P sub r is delta, and show that goes to 0. All right, so here's the formula again, just so that we have it in front of us. So the first point in the proposition that follows simply because if as long as you know we're in the disk, right? So that this makes sense. So the numerator is positive if you know as long as r is less than 1, and the denominator is it's actually also positive, right? Because well, we get the denominator here, and now we can sort of, well, what's the smallest that it could be? Well, it's smallest when cosine is 1, right? So so it's this. Well, this is precisely the square of 1 minus r, and again, as long as r is less than 1, then this is strictly positive, right? So we actually have that p sub r, it's positive number over a positive number, it is positive, right? So for part 2, that we integrate to 1, well, let's just integrate, right? So let's plug in yet. Let's use the second version of this, the second formula. Now, if we rewrite, we can pull out the real part outside and just integrate whatever's inside. And over here, I've added I've added an I over here and an I over here, right? And then r e to the I theta, r e to the I theta over here. Now, why did I do that? Well, because over here we have dz, right? So if we write out, we put in the dz, we put in the 1 over z, right? So that's the z, this is the dz, and then this guy, you know, if we're going around, instead of minus pi to pi, we're going around the disk of radius r, sorry, I forgot to mention that, then this guy is 1 plus z, 1 minus z. Okay, well, now we're essentially done, because now this thing we know how to compute. We have Cauchy's formula. It's this guy over here in the top evaluated at 0, right? Well, and at 0 it's 1, and we're taking the real part, but it's actually equal to 1 anyway. It's already real, right? So we get that this is 1 by Cauchy's formula, right? It's maybe an unexpected version of Cauchy's formula, but we've seen those kinds of integrals before. Okay, so for 3, you basically do what I said before. We only need to prove it for the positive interval, so from delta to pi, and on 0 to pi, p sub r is strictly decreasing, and it just follows from the formula. And so we need we only need to show that p sub r of delta is going to 0. So the function, if we think of now, let's look at what's inside. Well, well, it's inside there. So this thing, if we, it's just the only difference is we're plugging in delta, right? Oops. So we're plugging in delta for theta, right? And we look at this function over here as a function of r, so delta is fixed, right? And that's continuous because delta is some positive number, right? So this never blows up, right? This is never, the denominator is never 0. So it's continuous at r equals 1, and so we can just plug that in, see what's the this function is at r equals 1, right? And well, it's we make the denominator real, right, by multiplying by the complex conjugate, right? So we get well, we get this. It's the modulo squared, right, on the bottom, and on top we're really getting this. This is almost like the imaginary part, except for the 2i. We're not dividing by the 2i, so it's this thing, right? Well, why did we say that we're done with this proof? Well, because what did we prove? We proved that at r equals 1, this function is purely imaginary, right? It's some real number over some real number, so that's a real number, times I, right? And so the real part is 0, right? And the piece of r is well, who cares what this is, but it's a real part of this guy, right? Okay. Now that we have this proposition about how the Poisson kernel looks, how it behaves, some basic properties, we can now show that we actually have a solution to the Dirichlet problem in the disk, right? So suppose that we have a continuous function on the circle. Then we define this p sub u. P sub u, p of u. So this is this Poisson transform, Poisson integral. We're going to define this function on the entire closed disk, right? And we're going to define it first inside. So if at r e to the I theta, as long as r is less than 1, so if we're inside the disk, we're going to integrate u against the Poisson kernel. We're basically doing a convolution with an approximate delta function. It's something that comes up quite often in analysis. So we're integrating u against this kernel, and we're sort of shifting this peak, right? And basically the idea is that as r becomes higher and higher, then this peak is picking out only a smaller and smaller neighborhood of theta, right? And so we're averaging u around e to the I theta, and we're averaging over smaller piece, and so we're expecting that as r goes to 1, that we get u, right? And well, this would be if it's just any old delta function or approximate delta function, but this guy is will actually give us a harmonic function, right? It's not just the approximate delta function, but it's one that gives us harmonic functions inside, right? And so it's harmonic indeed. That's actually the easy part of this proof. The continuity up to the boundary is the harder one, right? It's always, boundary regularity of things is always the tougher problem, because, well, it's that's where we can't quite, it's when things blow up, right? As r goes to 1, this guy has, we're going to this pole, right? So this starts blowing up, right? So it has to be, has to be more care taken for that, right? So okay, so let's look at some z. So z is r e to the I theta, and for fixed t, we look at this kernel that we're integrating against, and we write it using the second form, right? That's 1 plus z, 1 minus z. But now it's there's a theta minus t in there, right? So there's this minus t. It's not really 1 plus z, 1 minus z, right? What does that do? Well, I can just factor out a z and or maybe factor out an e to the it, whatever, however you want to think of it. But we have this formula for it, right? It's almost the same thing. It's just we're rotating the z, basically. That's what we're doing. And so we're basically moving that peak around. That's what's happening, right? So now this is a harmonic function of z, right? I mean, this is for any fixed t, right? This is holomorphic function of z. So the real part of a holomorphic function is harmonic. Okay, so we have a harmonic function as a function of z in the disk, right? So if we differentiate under the integral, if we look at pu, right? So we look at pu of z, which is pu of r e to the I theta, and this is given by this formula, right? And now we can differentiate this under the integral. Well, maybe it's not clear from this form, but if we plug in this form of the Poisson kernel, we get this formula, right? And now if we can differentiate under the integral, right? Everything is nice and this is just the standard Leibniz rule for differentiation under the integral, right? Everything is nice and continuous and all that, because z is inside the disk, right? So this never blows up for this integral, right? So everything is nice and continuous and differentiable and blah blah blah. All that nice stuff that you need to differentiate under the integral. How do we differentiate? We're basically taking the Laplacian, right? So if z is x plus iy, you differentiate twice in the x, twice in the z, right? That's what you do. But you notice that there is no z on this bit of it, right? So when I differentiate under the integral, I'm only differentiating in this thing, and that's harmonic. And by definition, harmonic is that the Laplacian kills this guy, right? So it must be that the Laplacian of pu of z is also 0, so p of z is harmonic, right? For z in the disk, right? All right. Now let's rewrite things a little bit. This is sort of standard. If we have convolution, there's always two ways of writing the same convolution. Here, this is for periodic function. So if you do the change of variables over here to get from here to there, you would get slightly different limits. But everything is 2 pi periodic, so you can move those limits back to minus pi, right? You're always just after the change of variables, you're just integrating over some interval of 2 pi, so you can you can move that by the 2 pi periodicity of both this function as a function of t and this function as a function of t. They're both 2 pi periodic because if you in the formula this guy came up with that cosine, right? That's 2 pi periodic, right? All right, so let epsilon be given and let m be the supreme of u on the circle. U is uniformly continuous, right? As a function on the circle. I mean, the circle is compact, so u is uniformly continuous. And so there exists a delta such that we get the following estimate, right? basically whenever t is small, so less than delta, then theta minus t and theta are close, they're delta close, and so we can make it less than whatever epsilon we want. So we pick a delta such that this is less than epsilon over 2. Now, for some other delta prime, it doesn't have to be this delta. You could always, if you wanted to, you could make it a delta if you really want to. So there's basically for a large enough R, right? We can make this is that third guy in the proposition. We can make on this interval. These two intervals really. We can make sure that this is true. That we can make PR arbitrarily small uniformly as long as we stay away from 0. So for that fixed delta, we can make this true, right? We can pick another delta. Delta prime such that if R is within delta prime of 1, this is true, right? So now this is a fairly standard trick of how to get a constant into an integral, right? So I want to get this into an integral that looks like that looks like this, but this doesn't have an integral in it, so I write it as an integral basically because the integral of the Poisson kernel is just 1, right? So it's just integrating a constant, right? It looks more complicated than it is. All right, so let's bound. How far is pu at r e to the I theta and u at e to the I theta, right? So this is it was the same theta, but r that is we're gonna let it basically be here, right? Between delta prime close to 1. So now using this formula, we can rewrite, right? It's basically we're just taking this and subtracting this, right? And we're taking still the absolute values, right? And they're both, that's the reason why we changed variables here, so that we had the p sub rt, so that it's basically the same as over here, right? So that it factors out in this in this formula over here. Now, this we can't bound this integral all at once, as we have to bound it differently at different points. It's really there's really two different bounds. We're gonna bound these two integrals first. Actually, we're just gonna bound this one. This one is exactly the same, so it doesn't really matter. So we're just gonna bound one of these, and we'll say similarly the other one. Not the 3 dots is that's just whatever's in here, right? I just it wouldn't fit if I put all of that in there, right? So we're gonna bound these two separately, and we're gonna bound this separately, right? Because these first and the last integrals, those guys we can bound by this fact that p sub r can be uniformly small if we stay a delta away from the origin, and then over here p sub r is big, so we have to take another tack, right? But most of the mass of p sub r is going to be here, and that's going to be important. It's basically the integral of p sub r over minus delta delta for large enough r is it's almost 1. All right, so let's estimate these separately. So let's start with the first one. So we have this is just what it is. That's this first integral, and We estimate by just this triangle inequality for integrals. P sub r is positive, so we don't need the absolute value on it, right? And now we use before we just say, well, we'll just make this true, and it was just some random constant, right? Now we see why did we pick this constant over here, right? We could have made it anything we wanted to. So now we see why we made it this magic constant over here. So it's this thing. This thing is going to be less than this magical constant, right? And this first thing we're just going to bound by just the completely stupid estimate. U is at most m, and so the difference of u at 2 points is let's just bound it by 2m, right? That's a really stupid bound. It's probably much better, right? But here t is rather big, so these points are not necessarily close, so we don't really have any bound on this, right? Any reasonable small bound on it. But we have a large bound. That's fine, and we picked everything so that the Poisson kernel is arbitrarily small, so it can kill however large this is. It's probably not as large as 2m, but it's at most 2m. That's possibly a large number, but we don't really care because we can make this p sub r arbitrarily small uniformly on this interval over here, right? And then, well, this is the just the length of this interval, but that's that will cancel out this pi. I mean, delta is something small. We might as well just estimate this by pi, right? And then we just get what do we get? Epsilon over 4, right? So this first integral is bounded by epsilon over 4. Actually, even strictly, but that's not important. So the integral from delta to pi is exactly the same. The only thing that will change is these minus signs will disappear, and otherwise everything is exactly the same, right? It's the same exact computation. All right. So now, those are the two outside ones. They're both epsilon over 4, or at most epsilon over 4. So let's look at the inner one, and here we have to use a different tag. Here, p sub r is big, right? But this is small, right? Or this is we have control over how small it is. That's how we picked delta, right? But p sub r is big, but its integral is 1, right? So we estimate in the same way. First step is the same, and now we have an estimate on this guy that is small, and we make it epsilon over 2, right? That's how we picked. That's how we picked the delta, right? So that because this now t is small, it's between minus delta and delta. So theta minus t is within delta of theta, right? So here we're using the continuity of u at theta, right? Actually, at any theta, it's a uniform, uniformly continuous, right? So, well, if we have this integral, right? Everything's positive, right? What's under epsilon is positive. P sub r is positive. So we can just replace these deltas with pi's, right? Let's just at most get something bigger, right? And now, well, now this is this is just epsilon over 2 because the integral from minus pi to pi of p sub r is 1, right? Now it seems like we're sort of throwing in a whole bunch, but really p sub r is really small, and including the integral. So this is going to be close to epsilon over 2 to begin with. So So it's not such a terrible estimate actually. But anyway, we don't care. It's it's bounded by epsilon over 2. That's the only thing that matters, right? So if we have this this r is within delta prime, then the pu and u, well, at the same eta I theta, right? But here we have the r, right? So we're sort of going in radial directions. Then this is less than epsilon, right? And this was true for all theta, right? So what does that mean? That means that this guy, pu of r eta I theta, goes to u eta I theta uniformly as r goes to 1. Now that's not quite saying that, I mean, it's a different statement than saying that pu, because the definition of pu at eta I theta is just u, right? It's not quite saying that pu is continuous. We'll be able to prove that it is, but it's not quite the same statement, right? I mean, this is some limit along radial lines, but it's uniform. And that's going to be so it's going to make it work. So to prove continuity, well, let z naught be well, let's write it as eta I theta naught at some point on the circle, and let epsilon be given, right? Different epsilon than before, right? I mean, so u, which is really pu on the boundary of D, that's what we're looking at. This is continuous, so we can pick a delta, again different delta than before, such that that we have this is really u, pu and u are the same on the circle, right? So such that pu eta I theta minus pu at eta I theta naught is less than epsilon over 2 when, so we're thinking of it as a function of theta. So when theta and theta naught are within delta of each other. So this is again uniform continuity, right? Now we can also make, I mean, we could make, once we have some delta, we can also make it smaller, and we're going to use this this uniform convergence, right? That's over here, to say that, well, once r is bigger than 1 minus delta, then well, we have a convergence uniformly, so we can bound pu on at r eta I theta and eta I theta, right? So this is really sort of you can think of it as going, we're really trying to go from r eta I theta to, right, we're trying to go from here to here, and we're doing it in 2 steps. First, we go from here to eta I theta, and then we go from eta I theta to eta I theta naught. All right, but we have a bound for both of them, right? So as long as z satisfied is this in this sort of polar box, right, around theta naught, so that's the same as close to eta I theta naught, right? Z is close to eta I theta naught. I guess you could compute exactly what the what's the distance, but as long as z is this close to eta I theta naught, then you get that just by triangle inequality, classical thing is this thing is bounded by epsilon, and therefore pu is continuous at z naught, right? Which is what we wanted, right? Pu is equal to u on the boundary, and we're saying that pu is continuous, right? So you can see that that's the the second bit, the continuity, is actually that's the tricky business, because well, there are things blowing up, so it's you can't quite just start taking limits of things. You have to show something. Right? We're really showing that we can take this limit as z naught goes to eta I. As z goes to z naught. Right. All right. Well, so now we have that theorem, right? And we could rescale things, and we could translate things. Oh, there's a typo in here. I just noticed this. There's, of course, this is not u at r eta it. There should be a p plus r eta it. Sorry about that. Just like it's everywhere, here. So it needs to also go here, right? So here, right? So sorry about that. I'll fix that in the notes. So it's basically we just rescale, translate and rescale the solution in the unit disk. So it's actually basically almost the same. You just have to rescale the R. The translation doesn't really do anything. And so this is again harmonic inside the disk and continuous on the closure, right? So it's just what we've proved was basically p equals 0 and capital R equals 1. All right, now what we get is we get a representation of harmonic functions in a disk, the values of the circle. Now, why do we get that? Well, it's really because the Dirichlet problem is unique. The solution is unique, and this gives us the Poisson integral. This formula gives us a holomorphic function with those boundary values. Well, that means that if we have some harmonic function with those boundary values. Well, so if we have any harmonic function, then if we restricted the boundary and solve the Dirichlet problem, it has to give us that function again, right? So it reproduces harmonic functions once inside the disk once you know the values of those functions on a circle, right? So that's going to be very useful. Right? It's basically just like the Cauchy integral formula. It's that we get for in this case for a circle. Now there's one sort of downside with this. The kernel changes with the domain, right? In this case, it's a circle, and even here, as the circles, if the circles change, the kernel changes. I mean, for circles, it's not too terrible, but it does change, right? There is you could for different domains you would have different kernels. You could make a kernel for a square. You could make a kernel for an ellipse. You could make a kernel for some other domain. It's generally they're going to be sort of hard to figure out unless you can figure out some nice mapping from the disk to your domain. But it's the point is that here you need to know the domain to know the kernel. For the Cauchy integral formula, it was always just 1 over zeta minus z, let's say, right? It was the same. You're always integrating against the same thing. So that's an advantage of the Cauchy integral, right? Well, but the Cauchy integral is for holomorphic functions, right? So here we're talking about harmonic functions. Now, holomorphic functions are also harmonic. Okay, well, maybe that's not quite right in the way that we defined harmonic functions. They're complex. Holomorphic functions are complex valued harmonic functions, right? They're still killed by the Laplacian, and it's really because the real and imaginary parts are harmonic functions. So you can basically apply this formula to the real and imaginary part, but that just goes inside the integral, right? So integrating a complex valued function is just integrating the real and imaginary parts separately, right? And the Poisson kernel is real, right? So so basically you could all of what we did would actually work with complex valued u, right? And we get complex valued harmonic functions, right? So you could actually use it to reproduce holomorphic functions too, and this does this is sometimes useful. Now notice also, and this is gonna come up later, that if we plug in little r equals 0, so and here I didn't make the typo, all right? Here is the p plus, right? But if you plug in r equals 0, you just get the Poisson kernel is going to be 1, right? Let me show you the if I can find. So over here, if I plug in, well, it's going to have this 1 over 2 pi, but this bit of it, if I plug in r equals 0, this bit of it is 1, right? So so the Poisson kernel is going to be 1 over 2 pi, and so I'm going to get this 1 over 2 pi coming out, but whatever's else stays here is just just 1, the rest of it. So what is this? This is the average of u on the circle of radius r around p, and we're saying that it that equals the transform, the harmonic function inside, and because this just reproduces harmonic functions, this is actually a property of harmonic functions. Harmonic functions are equal to their average on a circle, right? That is what we said, I guess a couple of lectures ago. So it's we get this sort of mean value property, and we'll see it we'll see it a little bit more. And actually, the mean value property characterizes harmonic functions, and it's much easier way of characterizing harmonic functions, because this computing an integral like this is much easier. You only need, well, you don't even need continuity, but I suppose just continuity of the function is good enough to compute this. So checking that some equation like this holds is much easier, and actually turns out that that's sufficient. It's much easier than differentiating. Differentiating is hard unless you have a nice formula already. But if you have an ugly formula, integrating is easier, right? So okay, so we'll get to that later. All right.